Welcome to Hartman Math. Today we're going to take a look at solving trigonometric equations. Prior to that, a little practice on verifying the trigonometric identity. Go ahead and pause the video here and verify. We're going to take advantage of the left side, although it really wouldn't matter which side you worked on. The amount of work is about the same. Work on the left side, it being the more complicated denominator, the binomial. We're going to work on that side. I think we're going to start with conjugate. And so we're going to multiply these together. Now on top, I would definitely leave that factor to not distribute. But on the bottom, we're going to have to multiply that out. And then we have a Pythagorean identity right there. And if we just cancel cosines, top and bottom, we're going to be left with 1 minus sine theta over cosine theta. We've got our match and we have verified. All right, 5.3, solving trigonometric equations. For example, sine of x equals 1/2 as a trigonometric equation. We can kind of see, we can take a look at the graph here that we've worked on back in chapter 4. And we've got the line 1/2 right there. So graphically, we would have solutions where those two curves intersected, which is here, 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 here. But what we've seen here is we've kind of broken this down into kind of two parts. We've got this pi over 6, and then 2 pi later is pi over 6 plus 2 pi. If we went another 2 pi further than that, we would hit another point of intersection. Going backwards, pi over 6 minus 2 pi. So that means that pi over 6 plus any multiple of 2 pi times n, where n is an integer, would be a solution. And similarly, for 5 pi over 6, and 5 pi over 6 plus 2 pi, and then if we went further, 5 pi over 6 plus 4 pi, and over here 5 pi over 6 minus 2 pi, and 5 pi over 6 minus 4 pi, etc., because of the periodic nature of the curve, 5 pi over 6 plus any multiple of 2 pi, when we write that as plus 2n pi. And we do always have to stipulate, if we're having n be in our answer, that n is an integer. All right, example number 1. So we're going to always pay attention to the directions. When it says solve, it means find all of the solutions. And these are typically going to have an infinite number of solutions. So we use that algebraic notation to represent that. All right, so we've got, in this case, cosine x's on both sides. Let's see if we added a cosine x to both sides and then isolated cosines on the left. Maybe we could get the number on the right, so maybe also add root 3 on both sides. And then divide by 2 on both sides. So that's the first thing. We've isolated cosine of x. Cosine of x equals. And then we're hoping that that's going to be a unit circle value. So remember, cosine is the x-coordinate on the unit circle. So where on the unit circle do we have an x-coordinate of root 3 over 2, where we're going long and then short? So I think that's going to be at pi over 6 in quadrant 1. But also, where else is cosine positive? Quadrant 4. So I think that's going to be 11 pi over 6. So pi over 6 and 11 pi over 6. But we want to find all the solutions. So we're going to say pi over 6 plus any further rotation. So we say that as pi over 6 plus 2n pi. X equals 11 pi over 6 plus 2n pi. And anytime we're using n, we have to stipulate what n is. And this is the symbols that we would use. N is an element of the set of integers. You have to be able to write that correctly if you're writing it down on paper, because if you write it like this, that's not going to be accepted because that is not the notation. So if you are afraid you're not going to be able to write the correct notation, you could just use the words where n is an integer, because that is what this means. N is an element of the set of integers. Checkpoint. Notice the difference here in our directions. We only want to solve from 0 to 2 pi within one positive rotation. So we're not going to have ends in our answer. Then we would have typically a finite set of answers, and you could just list them all. So go ahead and solve on the interval from 0 to 2 pi. Pause the video here. All right, a similar thing where we're going to isolate sine of x. That's the y-coordinate, where we're going to have a y-coordinate that's negative and is root 3 over 2, so that's going to be tall going up, so short, and then long going down, and that happens at 4 pi over 3 and 5 pi over 3. We didn't use the ends because we're just looking for the finite number of solutions, and there are 2 of them, one in quadrant 3 and one in quadrant 4. All right, example number 2, extracting square roots. So we're going to isolate cosine squared x first. Maybe we add 1 to both sides and divide by 2 on both sides as a second step. And then we'd go ahead and square root both sides. Careful, there's 2 things that we got to be careful about there. One, how do we square root the fraction 1/2? It's just the square root of 1 over the square root of 2. And then the other thing is if we're going to square root both sides, we're going to need a positive and negative answer. We're going to get plus or minus. So we're going to get plus or minus 1 over the square root of 2 because the square root of 1 is 1. Now, if you want to rationalize that by multiplying top and bottom by root 2, it might look a little bit more familiar to you. Hopefully, we recognize that this is the same as root 2 over 2. So now we're looking for x coordinates that are root 2 over 2 that are positive or negative, meaning in all 4 quadrants. So solve means we're going to find all of our solutions. So we're going to need that plus 2n pi kind of idea to get all of the solutions. But now we're talking about in quadrants 1, 2, 3, and 4. So if we look at that, we could, root 2 over 2 is our 45, 45, 90 special right triangle. That's a pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So it is okay and acceptable to say pi over 4 plus 2n pi, 3 pi over 4 plus 2n pi, 5 pi over 4 plus 2n pi, 7 pi over 4 plus 2n pi, where n is an integer. Or we could recognize that all of these are equally spaced. If we just start at pi over 4 and add pi over 2, add a pi over 2, add a pi over 2, and add a pi over 2, then we're going to hit all the solutions anyway. So we could do the 4 of them, or more efficiently, we could just say pi over 4 plus some multiple of, we're adding pi over 2's. So x equals pi over 4 plus n pi over 2, and that's going to hit all of our solutions, where n is an integer. Factoring can be a strategy. Example number 3. This time we're going to solve on 0 to 2 pi, so we're going to probably just get a finite list. All right, so cosine squareds might be a good strategy for us as this being a quadratic equation. Get it equal to 0. Let's go minus a cosine x on both sides. And then it does suggest factoring, but we might think factoring anyways. Let's factor out a common cosine x. So if we factor out a GCF of cosine x, we're going to still have one more cosine x here minus the 1. Now let's split those apart, set them both equal to 0. Cosine of x equals 0. 2 cosine x minus 1 equals 0. If we then solve for cosine of x there, add 1, divide by 2. We're going to get cosine of x equals a half. All right, so where is the x-coordinate 0 on the in the unit circle? Straight up, straight down, pi over 2, 3 pi over 2. Where is cosine positive and 1/2, meaning short, and then going up tall on that one, so pi over 3 and 5 pi over 3. It doesn't exactly matter which order you list, but a lot of times you're going to see maybe the back of the book kind of an answer listed smallest to biggest. So you might have written, hey, these two are these two, and then this one is that one and that one, and the order really doesn't matter, but they've just listed it from smallest to biggest here. Example number 4, solve an equation of a quadratic type. 2 sine squared x minus sine x minus 1 equals 0. We might investigate factoring. It's already equal to 0, so that we have the benefit of that. Now, to kind of think about, maybe pause the video here, see if you can get this factored. Hint, it's going to be a binomial times a binomial. All right, it does work out if it's 2 sine x plus 1, sine x minus 1, as first and first multiplied together to make 2 sine squared x, last and last multiplied to give us negative 1. Outside, inside do make the negative 1 sine x in the middle. So if we set these equal to 0 and solve, on this one, 2 sine x plus 1 equals 0 becomes sine x equals negative 1/2. This one's going to become sine of x equals 1. Where is the sine of x negative? That's going to be quadrants 3 and 4. Where is the y coordinate 1/2? So that's going to be long going out, short going down. So 7 pi over 6 and 11 pi over 6. Where is the y coordinate 1? That only happens straight up at pi over 2. Okay, and solve. So we want all the solutions. We've got from here pi over 2 plus 2n pi. We've got 7 pi over 6. From quadrant 3 plus 2n pi, 11 pi over 6 plus 2n pi. We could write it like this, or maybe there is a more efficient way. Let's take a look at that. We've got straight up pi over 2. We've got 7 pi over 6, and we've got 11 pi over 6. Well, remember, this is also 3 pi over 6. So if we add 4 pi over 6, we get to here. If we add a 4 pi over 6, we get to there. And again, 4 pi over 6, we get back to a coterminal angle. So these are equally spaced, adding 4 pi over 6, also known as 2 pi over 3. So we could just start at this 1 up here at pi over 2 and add 2 pi over 3 if we wanted to and be a little bit more efficient. Add 2 pi over 3, add 2 pi over 3, keep adding 2 pi over 3's. So pi over 2 plus 2n pi over 3, where n is an integer. That's it for today. I'll see you next time.